Alrighty guys, so we've reached a point here on calculus now where we're going to begin talking about parametric equations, polar graphs, even vectors. So I'm making this video just to do a little, I guess, a crash course, just as a reminder of what parametric equations look like, how they work, how we can eliminate the parameter, etc., so that for next class you're able to then do the calculus that we want to do with parametric equations, like find derivatives, find tangent lines, etc. So this video is literally just a crash course over parametric equations. Now, remember, the parametric equations is basically two equations that represent a curve. So for example, I can give you the set of parametric equations as x equals t squared minus 4 and y equals t over 2. Now, this set of parametric equations represent a curve. So one of the things I'm going to ask you to do is for you to be able to sketch what this curve looks like. So what we're going to do is we're simply going to create a table. So now they're also going to give you some information. Now, because it's in terms of t, typically this is referring to time, or it really doesn't necessarily have to be time. It's just a parameter. They typically will give you a parameter. So for example, let's say that they want t between 3 and negative 2. With this information, we should be able to come up with a sketch, and to do so, we're just going to go back to good old Algebra 1 and create a table. So I'm going to create a table where you have t, x, and y, and I'm literally just going to plug in values starting from negative 2 to 3. So I'm going to go to negative 2, negative 1, 0, 1, 2, all the way to 3, and you got to plug that point into each equation. So if I plug in negative 2 squared is 4, minus 4 is 0. And then negative 2 here over 2 is negative 1. So we're just going to continue to try this. So that's negative 3. And that's going to be negative 1/2. And then we're going to plug in there. So that's going to be negative 4. And that's going to be 0. That's negative 3 once again. Interesting. And that's going to be 1/2. That's 0. And that's going to be 1. And then that's 9 minus 4, that's 5, and that's going to be 3/2. So what you've done is, now you've created a set of points. You have the point 0, negative 1, 3, negative 1, negative 3, negative 1/2, etc. So what we're going to do is we're going to plot those points and into the x and y axis. So we're just going to say we're going by 1. So 0, negative 1 is here. Negative 3, 1/2, so let's say that's there. Negative 4, 0 is there. 3, positive 1/2. 0, 1, and then we got 5 3/2, so 1, 2, 3, 4, 5. So then this thing looks like that. Alright. The advantage of having these parametric equations, not only do we get this curve that we have here, which as you can see, this would not be a function the way it stands right now because it would fail the vertical line test, but you can also tell the direction of everything happening. So because of this, if we go in order from least to highest, we know that we first started here and we are going in this direction. So the advantage of this parametric mode is we can get, it tells us a little bit more of the story, and it can also represent things that would not be able to be represented by a function. Okay? So I think you should be pretty successful at recreating this on your own when you try the homework tonight. The second thing that I'm going to ask you to be able to do is to take a set of parametric equations, so for example that one, and do something called eliminate the parameter. Okay, so what that means, if you think about it, I introduced the parameter of time here. So if we want to eliminate time, what I'm trying to do is I'm going to try to get rid of t. So instead of having two equations, it only becomes one equation in terms of y of x. So really what you want to do here is solve one of these equations for t and plug it into the other one. So what I'm going to do here is I'm going to solve this one for t. It seems like to be the simplest. So I'm going to take x equals t squared minus 4, y equals t over 2, and I'm going to solve this for t. So that means 2y equals to t. And I'm going to go into the other equation and substitute it in for t. So that means that x is equal to 2y squared minus 4. And if we simplify this out a little bit, that means x is equal to 4y squared minus 4, which if you think about it, it's kind of a parabola here, and it's going to be, if you remember conics, this is a parabola, right? A conics, remember, it doesn't have to be a function, but it's still a parabola, and as you can tell, we only sketch part of this parabola. We only sketch from -2 to 3, because that's what the parameter was limiting to us. So if we were to grab this, it would look exactly the same as this one, but it will actually continue going in this direction forever and continue in that direction forever. So eliminating the parameter kind of allows you to check your work per se, and brings you back to just good old functions in terms of y or x. Okay. We're going to try one more with eliminating the parameter, because sometimes eliminating the parameter is not that quite simple as these ones are, where you can just solve for t and plug into the other equation. Let's say that we have to do something where it has trig on it. So for example, let's say I give you something like x equals to 3 cosine theta, y equals to 4 sine theta, and we're going to use theta between 0 and 2 pi. Cool? Now, you may be tempted to do the same thing you did on the previous problem, which is just kind of solve for t, but we don't have t in here, we have theta. To solve for theta and then plug it into the other one. But instead, we can use our knowledge of trigonometry a little bit. I'm going to use my knowledge of identities from trigonometry. So the fact that I have cosine and sine, it makes me wonder, or basically remember from trig, that there's an identity that says the following: cosine squared theta plus sine squared theta equals to 1. And then there's variations of it. So we have, remember, tangent squared theta plus 1 equals to secant squared theta. We also have cotangent squared theta plus 1 equals to cosecant squared theta. We also have double angle identities like sine 2 theta equals to 2 sine theta. Cosine theta, we got cosine 2 theta, which is equal to, if you remember, several of them. We have cosine squared theta minus sine squared theta, or 2 cosine squared theta minus 1, or lastly 2 sine squared theta. Now, I'm going to be able to really use my knowledge of trigonometry to eliminate the parameter. Now, I listed all of this, but really the one that I'm going to focus on is this one for this example, since I'm dealing with sine and cosine. So what I'm going to try to do is I'm going to try to achieve a cosine square here and a sine square, and just substitute in. So what I'm going to do is first I'm going to get rid of this 3. So I'm going to bring it over by dividing. So I'm going to have x over 3 equals to cosine theta. And I'm going to do the same thing on this one. So I'm going to have y over 4 equals to sine theta. Now, I've isolated cosine and sine, which is kind of what I wanted to do. So now I'm going to go ahead and square everything on both sides. If I square everything, I get x squared over 9 equals to cosine squared theta. And I get y squared over 16 equals to sine squared theta. And now all you have to do is simple concept of substitution. You know that cosine squared theta plus sine squared theta is equal to 1. And according to this problem, cosine squared is equal to that. So I'm going to go ahead and substitute it in here. So I'm going to say x squared over 9. I know that y squared over 16 is sine squared, so I'm going to substitute it here. And as you can see, you've eliminated the parameter successfully. You've turned this into a function in terms of x and y. And if you really look at this and you remember, hopefully you do remember your conics, this would be an ellipse. This would be an ellipse with a center of 0, 0. And we can quickly sketch this out. So at 0, 0. And remember, this value right here, because it's underneath the x value, if you take the square root of it, it tells you how much to go left and right from the center. So the square root of 9 is 3, so I'm going to go 3 to the right and 3 to the left. And the square root of 16 is 4, so 1, 2, 3, 4. 1, 2, 3, 4. So this looks kind of like this. So you got an ellipse that looks in that manner. But by me graphing it this way, I'm missing some information. It doesn't tell me the direction in which this was graphed. So what I can do, if you were asked to give the direction of this, we're going to have to go back to parametric mode. But as far as eliminating the parameter, the process of using the identities is definitely going to be your go-to guide here, so that you can get it here. Okay? But let's say that you are asked for the direction of this thing. So we're going to go back here, and I'm going to use this information to help ourselves out now that we have the graph. So for example, I'm going to start at 0. If I plug in 0 for theta, cosine of 0 is 1. 1 times 3 is 3. And as you can see, I have that point right here, 3. So that's telling me that I'm starting here. So this is either going to go up or down, so I need to figure out another angle. Make your life easier and choose an angle that's easy to find the cosine of, like it's going to be a 1 or a 0. So the thing I can think of is pi over 2. Cosine of pi over 2 is 0. 0 times 3 is 0, which tells me then that I have the x-coordinate as 0. I'm sorry, 0 right here. So I could either be here or here. So I do need to figure out whether it's up or down. And for me to figure that out, I need to plug in pi over 2 into here. So the sine of pi over 2 is positive 1 times 4 is 4. So that's definitely up here. So according to the order, if I'm going from 0 to 2 pi, if at 0 I'm here, and at 2 pi over 2 I'm here, the direction of this has to be the following. Okay? Sorry, I know that the video's a little shaky. I'm just trying to do a really quick crash course. I don't want to overwhelm you because it is a lot of material to review, but I want to keep it as short as possible for you to try this homework tonight. Okay? I think this should give you a good starting point for the homework. Make sure that you practice, make sure that you do the homework, and that you're ready to go by next class. I'm going to assume next class that you know how to eliminate the parameter, that you know how to sketch curves, because what we're going to do is now we're going to do some derivatives, we're going to find tangent lines, we're going to find arc length, etc. Okay? Thank you for watching, and I will see you guys next class.